All right, welcome to Lecture 21b entitled Circulation and Flux, Vector Identities and Helmholtz Theorem. So this basically is a continuation from Lecture 21a, and we'll make use of some of the new definitions to explore the issue of circulation and flux a little bit more. The material for this lecture is also from Reading Assignment 4, Sections 1.9, 1.10, 1.11, 2.1, 2.2, and 3. The objectives are to compute the divergence and the curl of a vector field and understand their physical meaning, understanding vector identities, and Helmholtz decomposition theorem is perhaps one of the most important theorems in vector calculus. The concepts and visualization skills you can get from this lecture include an intuitive understanding of the divergence and curl of a vector field, understanding of vector identities, Helmholtz decomposition theorem, and then a non-mandatory section, about 2 slides, on the meaning of the symbol J, which is a unit pseudoscalar, and bold J, which is a unit pseudovector. As usual, the second slide is just a summary of the slides to follow, so we'll just move on. Okay, so the divergence and curl operators in 2D applied to the original field that we investigated prior to getting into details regarding what is a curl of a vector field and what is the divergence of a vector field. Recall that we had a total vector field which was x minus y for the x component, x plus y for the y component, and we had divided it up into two vector fields. One basically which we associate with a flux, which was x, y, and the other one which we associate with circulation, which was minus y, x. And so we now basically have the tools for computing divergence of curl, and this was the total field that we were dealing with at the outset. So the divergence basically in 2D is just a matter of setting the vector field with the z component to be 0, and if you apply this, we end up with the result which we'd already proven earlier. So it's the derivative of the x component with respect to x, the derivative of the y component with respect to y. The curl of a vector field, unfortunately, does not exist in 2D. And so what we have to do is to sort of create a falsified 2D vector from 3D. And the simplest way of doing that is to essentially assign 0 component to the z field, and to make sure that the x and y components of the field are only functions of x and y, and then apply the curl operator to this. If you do that, you'll end up with this as being the magnitude of the curl and this being the direction, which is out of the page. Okay, so this exists in 3D, but of course there's no such thing as z hat in 2D. But we've sort of worked around it by doing it this way around. All right, so now if we apply the definitions of divergence and curl according to this to the original problem, then effectively the divergence of the vector field applied to the total field is 2, and the divergence applied to the flux component of the field, which was just xy, 0, is 2, and the divergence applied to the circulation component, which was this value in 2D, will be 0. Okay, reminder that this was all defined in Lecture 21a. All right, this looks very similar to what we observed when we did a very simple calculation with no knowledge of what this divergence would look like in the first place. For the curl, we take the curl of the vector field. So this is a typical way of setting it up. The first row is going to be the unit vectors. The second row, the partial derivatives, which would be this one here. And the third row are the components of vector field, which is the third row. If you do this computation, you end up with 0, 0, 2, which is 2 in the z hat component. If you take only the flux component and take its curl, you'll end up with 0. If you take only the circulation component and take its curl, you'll end up with 2z. So it's very interesting here that if its field is pure flux and you take its curl, it's 0. If you have a field which is pure circulation, right, then its base divergence is 0. So these are sort of two different properties of a vector field. And so you would think that perhaps we can add them up together, and in fact that will be the subject of Helmholtz decomposition theorem. All right, so let's compare what we had originally done using a very simple approach where we used a normalized flux and circulation, and now look at the formal definition which applies across the board for the divergence of a vector field and the curl of a vector field. These, by the way, are the operators. So we've basically summarized what we had on the previous page. The divergence of field was 2, divergence of flux is 2, divergence of circulation was 0, the curl of the total field was 2. The magnitude was 2, but the curl was in the z direction. The curl of the flux component was 0, and the curl of the circulation component was 2z, but if we take its magnitude, it's equal to 2. All right. If you actually go back and look at the previous slide, we essentially see complete correlation here, right across the board. And so the only question is, what is the divergence doing? It's more or less picking off the flux component, and that may essentially give you some sort of idea of the strength of the source that's producing the flux in the first place. What does the curl do? It picks off the circulation component. So effectively it tells you what is the axis rotation and what's the magnitude of that circulation. Right? So that's what it's doing. So these are the concluding statements then. The divergence operator picks off the source, flux type behavior of the field F, and it's a scalar density representing the properties of the source. The curl operator picks off the rotational or circulation type behavior of the field, and the resultant is a pseudo-vector representing the axis of rotation and the normalized magnitude of circulation density. So this is more or less the takeaway message. All right, so now let's look at basically an interactive simulation highlighting the source type behavior of the field F. And again, we're restricting ourselves to a two-dimensional vector field because it's easier to visualize. But the basic ideas can be demonstrated. So what I've done here is plotted these arrows. These are blue arrows, and the field is XY, and these are going to have a radial type distribution, and the magnitude gets longer and longer as you get further and further out, but they appear to emanate from the origin. And so what I've done is if I created a position vector, which points to the center of this circle, and it can be moved around anywhere in this space and probing different locations in two-dimensional space. The variable slider P is the rotation of this position vector. This is a little arrow that just goes in a circle and maps out basically different points as you move around the circle. This is the unit tangent vector differential arc length that you see here, and this is the normal component, again pointing to the right. By convention, if you traverse in a counterclockwise direction, the normal points to your right. And the shaded circle area, right, that you see here is basically a specific color, and the brightness of the color would represent the strength of the source. So for example, if it was a very weak red, you might say that you see white, but if it's a very deep colored red, this will get highly saturated. So depending on the strength of the red, you could essentially say is the strength of the source. So just using color coding. In this particular case, the divergence is a constant, and so their brightness would remain constant irrespective of the observation point. So if I were to move this pink unit here to any other location up here, I would notice that the color doesn't change. On the other hand, if in fact we're dealing with a different vector field, then in principle the color would change depending on location, which tells you that divergence is a function of position. If you want to look at this simulation, you can just click on the link that you see here. All right, we can also basically look at an interactive simulation to highlight the rotation or circulation type behavior of the field F. And so in this case, I'm showing a pure circulation field, again in 2 dimensions, which is defined as follows. In this case, you can see the field lines basically form a closed circle. And of course, the magnitude or the length of these vectors get larger as you move further and further away from the origin. In this case, these field lines are in a counterclockwise direction. And again, similar to what we did for the previous case, we have a position vector that basically is positioned in such a way that it ends at an observation point. And about this observation point, we have this circle, and we have a position vector basically which just goes around the circle once completely. All right, and the red vectors that you see, these red vectors pointing upwards, basically represents the strength of circulation, which is magnitude. In this case, it's the brightness of the vector, and the axis of rotation, which is the direction of the vector. So the circulation is pointing in the z-hat direction, and the color basically takes on a certain value. If we were now to move this observation point, say, over here, and notice basically that the color is changing, that would indicate that the circulation is a function of position. The direction basically remains the same because this is a two-dimensional problem. And so it's pointing upwards in this particular case. All right, so now we just look quickly at some vector identities involving operators because we make use of these quite frequently, starting with some simple things which you already know. So for instance, A plus B is an addition operator that takes the two vectors A and B and adds them to produce a third vector C. Grad fx, y, z, the operator grad is just dx, dy, dz, which operates on a scalar function fx, y, z to produce a vector valued function f dfx, dfy, dfz. We now have two new types of operations on vectors, the divergence and the curl. So the divergence of a vector field A, D, the dot is a dot product operator that takes the vector dx, dy, dz, and the vector A, which has an x and a y and z component, and performs a dot product operation to produce a scalar function rho. So the partial with x operates on ax, the partial y operates on ay, and the partial of z operates on az. And because it's a dot product, you're adding up the results. And so this summed together is a scalar function, and we're going to give it the symbol rho xyz. It tells you basically the magnitude of the source at some given point. Right? And of course, it can vary, or it could be constant, depending on the nature of the problem. Lastly, the curl of the vector field. The cross mark is a cross product operator. It takes the vector and the vector, which is a gradient operator, and the vector A, which is an x and y and z component, and forms a cross product operation to produce a vector valued function f. And so again, whenever you see something of this nature, the first row basically is going to be the unit vectors. The second row are the partial derivatives, which is tied to this. And the third row are the components of the vector field. If we take the determinant of this, then you'll have a z component. You got, an x component, a y component, and a z component, and this would be the total field that you're left with. All right, here's some more examples. So if you took the divergence of the curl of a vector field, you get 0. So this is an indication that you have a source-free field. This is an important identity. And so you can prove that. The divergence operator is this. The dot product is here, and the curl basically is what we had computed on the previous page. So you basically apply this to both terms here, this to both terms here, and this to both terms here, and expand out. You end up with this, and you'll see that you get terms basically canceling each other out. So for example, this term, dx dz and dx dz, they cancel. So pairs cancel and you get 0. So we just proven. Another possibility is, for instance, a rotation-free field. If you take the curl of a gradient of some scalar function, it's equal to 0. All right, so let's prove it. So if we take, for instance, the gradient of phi, that's this, and we're now going to take the curl of this. So again, the definition of curl basically in matrix form is to take the determinant of this matrix, the unit vector. First is the partial derivatives, and the second of the partial derivatives of the actual scalar function. If you perform this, then this is going to be the x component of the curl of the vector field, the y component, and the z. But if you look at this, each one of these terms is 0, and so this is a 0 vector. Lastly, we have what we call the scalar Laplacian. If you take the divergence of the gradient of a scalar function, then here is the gradient operator. It's a dot product, and this is basically the grad of phi shown here. If we now basically apply this on this, this on this, and this on this, add the results, you end up with this. And this in short form basically is given the symbol. This is the Laplacian operator operating on a scalar function. All right, a couple more. This is a vector Laplacian, or what they call Lagrange's formula for the delta, the Nablus symbol here. So let's take the gradient of the divergence. This is a scalar. This is a gradient operating on a scalar, which is a vector, minus the curl of A. And this is more or less a Laplacian of operating on A. That just means that you're taking the second derivative of the x component second derivative of the y component, and second derivative of the z component, and forming a new vector. All right, let's prove it. Divergence of A we can basically prove. Here's the Nabla operator or gradient operator operating on the components of A. You ends up with this expression. If you take the gradient operating on the divergence of A, that's gradient operating on this, then this would be partial of x operating on all three, which would be the x component, partial of y on all three to produce the y component, partial of z operating on all these three to produce the z component. So these are the components of the resultant vector. Last thing is to take the curl of the vector field A. So the curl of the vector field A, here are the x, y, and z components. Now we take the curl of this. A lot of bookkeeping. If you do that, then this is the resultant for the x component, for the y component, and the z component for this vector field here. Now if we take these two, that's this one and this one, subtract this from this one, which means you'll change the sign on this one, we'll end up basically with an expression that looks like this. And you'll notice here, this is just treating ax as basically it's just a scalar function, but this is the Laplacian operator operating on ax, this is the Laplacian operator operating on ay, and this is the Laplacian operator operating az, but this is a vector. Okay, so this is what we call the vector Laplacian. Okay, so now this brings us to the last major topic, and that's the preliminaries to Helmholtz decomposition, and we're going to illustrate by way of a 2D example. So, for instance, any vector field F is the superposition of a field which is circulation-free, which means it's a flux vector, and a field which is source-free, which is a circulation vector. So I've written it out as the sum of the two. And since it's two-dimensional, that means that the x and y components of this vector field can only be functions x and y, and the z component is 0. The reason I write it this way is because I want to basically exploit the curl operator, which only has meaning when you're talking about a three-dimensional vector, a vector in 3D. So the curl and divergence of the circulation, if I take the divergence of the circulation vector, I get 0. We already have the identities that we dealt with. And I have the curl of the circulation vector. I'm going to give this basically a symbol j. This is a vector field. We've already gone through this example in 2D, and we found that this is just going to be dgx minus df by dy, and in the z hat direction. And the curl and divergence of the flux component of the vector field, the divergence of the flux component would be rho xy. This is a scalar function, and this turns out to be df dx plus dgy. All right, you can basically show that, whereas the curl of the flux component was equal to 0. Okay, so just to clarify, the item marked in yellow does not exist in 2D. Okay, this z hat has no meaning. So what we've done here is we created a fictitious z-axis so as to apply the curl operator. The axis of rotation, we call it a pseudovector. In geometric algebra, we'll just quickly discuss, the term dgx minus dfy z hat would be replaced by something that looks like this, where this j, bold, represents an imaginary unit pseudovector which is aligned with a fictitious z-axis. And it's related to the magnitude of the circulation density. So this is related to the magnitude of the circulation density. But by putting in j and you make no inference to a z direction, you just say it's some form of pseudo-vector. Okay, so the formal definition of Helmholtz decomposition theorem, which now applies in 3D as well, and the computation of F flux and F circulation. So the general statement I'm making is that any vector field can be written as minus the gradient of a scalar function plus the curl of another vector, which we call a vector potential. Okay? So this is the general formulation. The proof is given in one of the appendices in assignment 4. It's not necessary to go through it, but nevertheless, this is a true fact. So F flux we call a conservative field or an irrotational field. These are just names given to fields that have this behavior. If it's just a field which has got circulation, then it's a solenoidal field, or also called a source-free field. Notice that if we take the curl of this expression on both sides, the curl of a gradient of a scalar function is 0. We've just shown that to be the case. Okay, so if we take the curl of a flux, right, curl of grad phi equals 0. All right, if we take the divergence of a circulation component, which is this term, we know that from a vector identity, this is equal to 0. Okay, and so by applying the operators, we're picking off these two terms independently of each other. Okay, so just a general note, there are an infinite number of ways to select phi and A given F. The question then becomes, how do we obtain phi, the scalar potential, and A, the vector potential, given F, and under what conditions are the solutions unique? The answer to this question is partly provided in sections 4.5 and 4.6, but you're not responsible for this material. If you want to read up on it sometime in the future, you feel free to do so. There just isn't enough time in this course to go into more details. This is the main issue, though, is that you can basically prescribe any vector field as a combination of an irrotational field and a source-free field, sometimes called a conservative field and a solenoidal field. All right, so it's a general notion that F flux and F circ can be computed once phi and A have been computed. So there are general techniques for doing that. Earlier we had defined F flux equals grad phi. However, in formulating the Helmholtz decomposition theorem, the -1 factor is a natural outcome of the theorem. I mean, this is basically what the theorem states. Nevertheless, any scalar multiple of grad phi is still an irrotational field. Now, the last two slides are not mandatory. This is not to be tested. This is some general information. And so I just want to quickly make a point here. So we're looking at geometric properties, pseudoscalars, and pseudovectors. So if you took a point, an object, all right, points exist in 1D, 2D, and 3D space. If we look at a line as an object, a line exists in 2D and 3D. If we look at basically a 2D plane, it's a 2D object. You have an oriented plane that exists in 3D. And of course, you can keep on going. You can go to volumes in 3D. And of course, there's something here, but we couldn't visualize it. Okay, and now what about differentiating between pseudoscalars and pseudovectors? So a pseudoscalar, for instance, AJ is a pseudoscalar. Recall that J dot J is -1 and A is a scalar. Now, if a pseudovector, we can write it in two different ways. Option 1, we can say A, some scalar, times J. J, we said, was a pseudovector. And it basically defined the direction of axis of rotation. And its magnitude A was circulation density. This is a formulation that's used if the axis does not exist in the number of dimensions being considered. Another option is pseudoscalar is to write J times A. J is a pseudoscalar, but A is a natural vector. All right, J defines the direction of the axis of rotation and the magnitude of the circulation density. Okay, the fact that basically we're dealing with the curl of a vector field, it is a pseudovector. So in 3D, we can do the computation, but to make it into a pseudovector, we multiply by a pseudoscalar J, and so now this by definition is a pseudovector. The last slide is just a quick summary of an overview of what we call geometric algebra. This is where the notion of pseudovectors and pseudovectors basically are unified. I've just put this slide here just briefly to indicate the parts which are related to pseudoscalars and the parts that are related to pseudovectors. Again, you're not responsible for this material. You can see how complex numbers come into the picture, and you can also see, for instance, how the Helmholtz decomposition theorem basically comes into the picture. And so it's for your interest only, and we'll just leave it at that. Anyways, that concludes Lecture 21B. Thank you for listening.